All right. Is my screen visible?
Yes.
Okay. Okay. So let's begin. So this week 8 is all about policy gradient method. So in contrast to value function methods, where we try to compute the value function and then try to find out optimal policy, instead of that, we directly try to find out the policy. Okay. So so week 8 is about policy gradient methods. Okay. Now, what are the benefits of policy gradient methods? One is that, of course, we don't have to compute the value function for every state, and that's not that could be a little bit problematic, as sir explained with an example. That for certain cases, for example, for inventory management system like such a problem where uh, you have to decide what you have to do if for example a certain article count of an article is less than, let's say, some threshold, right? Some threshold. If it is less than that, then go ahead and order it. Otherwise, don't order. So for problems like this, policy method, uh, policy gradient method, not policy gradient method, but directly manipulating the policy would be better, because if we go with the value function based approaches, then for every value less than c, uh, you will have to compute the value function for that and then come up with a policy that try to avoid that state. Okay. Few other uh, benefits that sir has mentioned in the lecture are they lead to simpler problem, not problem, but the solution description. Right? Because we directly store just phi a given s. Uh, there's one more benefit of this, which I don't think we have seen this kind of situation so far, which is they perform better in case of partial observability. Does anyone know what is partial observability?
I mean, maybe we can like the state that are more near might be visible. Some are maybe restricted. The other states are longer still. In a gameplay scenario, maybe is that true?
So partial observability is like when you are in a state but you don't know all its features.
Okay.
That's called partial observability. So you cannot be sure which exact state you are in. Okay, there might be multiple states. If your agent is there, it might feel like that. Okay, the agent might think that it is actually in the same state, even though they are different state. But since you are able to only partially observe the state features, that's why it might have that confusion. So partial observability means you don't have access to all the features of a state. So this kind of situation we have not seen so far in the course, but good to know that uh, policy gradient methods uh, are actually robust to partial observability. Okay. Coming back. Okay, a few more advantages that sir mentioned in the lectures is it has better convergence, uh, right? Better convergence. All right. So now before we now how do we the point comes down to how do we learn the policy directly, right? So the fundamental idea behind policy gradient methods is you use gradient of policy to change the probability of okay. So there are multiple things which are connected right now. So before we move on, I'll just draw the uh, uh, linear regression version that we studied the normally study in machine learning is something like this, that this is your cost function j theta. Okay, this is your theta, and you try to so j theta typically identify as the error, cumulative error that you want to decrease, right? So that's a measure of overall error, and you want to decrease it's parameterized by theta. So you want to find out this point, right? And what you try to do is you arbitrarily initialize theta so that you are somewhere on this curve, right? So let's say you are exactly this position. So you arbitrarily started it, and this is the place you start with. And what is the idea behind this? You compute a gradient at this point. I should use different color. You compute a gradient at this point, which will point to this direction, right? Go in the y-axis, towards the y-axis, towards upwards. And then you try. What you do is you move always in the opposite direction of the gradient. That is, you want to move downward direction because you want to minimize it, and that's why typically your update rule would look something like this. Not update rule maybe, or by alpha, and there is a minus sign over here because so this is the quantity which is going away from the minima where we want to reach, and that's why we put a minus sign over here. Okay, so this is what your change in theta looks like. Here the problem is quite opposite. Okay, so for before we move there, first of all, within our context, we need to find out j theta. What is the objective function? Okay, so this is how we define it. J theta is equal to expectation of R. That is your reward, right? So this is our objective function, and mind that instead of decreasing it, we want to increase it. We want to find out theta so that this quantity is maximized. So far, any questions? All right. So,
Yeah,
yeah, go ahead.
and I'm saying it's clear.
Sorry.
Um, it's clear to me. I was responding to this.
Okay. Okay. So let's move on. So whatever the update rule we are going to write, it's going to be something like theta plus alpha, which is our learning rate, nebula j theta. Okay. If it were linear regression kind of situation, there would be a minus sign over here because we are trying to move towards the opposite direction of theta. But right now we want to move to exactly in the direction of our objective functions gradient. Okay. All right. Now, before we come to this point, before we move forward, how we are going to represent our policy, right? So there are three cases, three different ways we can use. So two are discrete. So let's say we have discrete actions. One approach could be your softmax approach. So pi of SA could be e raised to the power theta a s summation of e theta s b. So this s parameter only indicates that we are talking about state s. There could be multiple different states, so that's why we append it with s. So what theta a is the probability, is the parameter which decides the probability of taking action in. So you can see that this is the softmax approach that we saw a long time back. So this is one approach. Another approach for discrete actions could be that pi of a given s is some parameter rho. I'm using the same terminology that sir is using in his lectures. A such that one. So sum of taking all the probabilities is going to sum up to 1, and each individual probability has to be written equal to 0. Okay, this is second way to represent policy. What is going to be the third way? Third way is if the actions are continuous. In that case, we represent action. Represent the probability of taking particular action as normal distribution of some normal distribution which is defined with some parameters mu and sigma. Okay. Any questions so far? All
No.
right. All right. Okay. So let's move on. Now, before we move on to computing gradients, let's take a simple example of, instead of there could be an episodic task from which your agent learns. Instead of doing that, we go with the simpler approach that we have a multi-arm bandit. Let's take the case of multi-arm bandit and try to compute the policy gradient for multi-arm bandit. Okay. Now, what will be the so this is theoretical and we are not going to use it, but it's worth noting. Sir also goes through this and explains everything. So let's take a look at that. Looks really bad. I'm going to just write A. Okay. So for a multi-arm bandit problem, if there is some policy, right, and it is parameterized by theta, then its expected reward would be. Can anyone try to guess it? Okay, so imagine that there are three arms. Okay, arm 1, arm 2, arm 3. The probability of them are 0.2, 0.3, and 0.5. And they have some rewards. Let's say I'm just writing them Q1, Q2, and Q3.
It's then I weighted of Q1, Q2, Q3.
Right,
Like
absolutely right.
0.2 by
Right.
3 again, I believe.
So 0.2 into Q1 plus 0.3 into Q2 plus 0.5 into Q3, right? Something like this.
Yeah.
Yeah. So this is in the form of example. But what about if I can? But I need to write it in the general form. So just taking the inspiration from this example, we can write this as sigma q for every action multiplied by probability of taking that action, right?
Yeah.
Right. And here I'm writing q star uh, because that's these are the q stars that I provided to you already. But we need to know the actual q stars for every action to get the expectation of reward. Any questions so far?
So Q star is the ideal one, right? Like I mean, on longer one.
No, q star the actual estimate
Okay.
of of taking action A.
Okay. Yep. Got it.
Yeah. Now, what I need to find out is derivative of this, right? Because if I find out derivative of this, gradient of this, then I can go back to my update rule and change theta as soon as I get uh, some samples. Or we'll come to the samples, but actually I need to compute the gradient of this, right?
So we will maximize this, right? Then maybe.
Yeah, we will try to maximize this, but before that, we need to compute its gradient so that we can use that gradient to
Mhm.
change the theta parameters theta in right direction, right?
Yeah.
Okay. All right. So now it's slightly tricky. See, if I had known these, probably computing this would have been easier, and probably I didn't need to compute it then if I had known the q stars, right?
Hmm.
But I don't know them, so I need to estimate them with samples. Okay, so before we come
Okay.
to this particular formula, how we are going to uh, change it so that we can estimate this with a number of samples. Let's talk about this for a minute. So if we don't have this, right? If I don't have the q stars, then what I do, I compute j theta with number of samples. So let's say I have n number of samples.
Hmm.
Ri I is equal to 1 to n.
Hmm.
Is that correct?
Oh, but I mean, maybe for multi-arm bandit that will be different, right?
For
Like if
multi,
we have 3 arms, every arm will have separate samples, right?
no. This is still for multi-arm mandate, and I'm generating all these RIs are generated by some policy theta,
Okay.
right? So see, instead of, since I don't have this, right? I don't have this. So yeah, go ahead.
I mean that pi of a theta might like policy might be missing, right? Like I mean probability where I get that reward.
Where you get that?
No, probability of picking that arm to get that
Okay.
reward.
Okay. See, so all these samples are generated with this policy, which is defined by parameter theta. You can assume that this is the case. That's the actual assumption, actually.
Okay.
Okay. Now I can write this thing in another form. Probably I should have written that first before coming here. So I can write this as expectation of reward under policy pi theta. Under policy pi, a more verbose method would be to call it expectation of reward under policy pi defined by parameter theta. We just call this pi theta. Does it make sense?
Yeah.
Okay. So from this formula, we convert it into an expectation, right?
Hmm.
And from this expectation, we convert into this formula from which, with the help of which, we can estimate it with number of samples.
Hmm.
Right. Same thing we are going to do with this thing also. Okay, but in order to convert it into expectation, I need to make sure that every quantity here, overall, yeah, in this formula, I have to make sure that there is some quantity over here by which I multiply, and this quantity sums up to 1, right, with this summation, right?
Okay. Yeah.
All right. So let's do. So I'm going to write j theta something like this. Q star of A I'm going to multiply it by pi theta A divided by pi theta A. Okay. Now think about this. This quantity sums up to 1 over all A, right? Now, if I want to estimate this thing with number of samples, I can do it because I can write it like this. Expectation of Q star A pi theta A pi theta A, right? Does it make sense?
For me, no.
Yes.
I mean,
Is it something like importance sampling?
Absolutely right. It's very much like importance sampling.
no, the theory makes sense, but what is pi theta a here? Like when it goes to the denominator.
This thing,
Yeah.
this is the probability of taking action A.
With the policy theta.
Yeah, with policy pi theta.
What is delta then? Like change in action.
This is the derivative with respect to theta.
No, in the sense of like looking at that state, what does theta make sense? Like, are we looking at the way we need to go, or to maximize it, or I didn't get that part.
Right. To see, this symbol is just a symbol for gradient, and right, we are trying to still, our goal is to change theta and thetas in such a way so that the expected reward is maximized.
Okay.
All right.
Yeah, you can go on. Like, we'll come back. Maybe I might get it after.
Okay. So, are you able to make the transition from this to this?
No. Mathematically, yeah, it makes sense. That's fine.
Okay.
Like in a scenario, I couldn't imagine that situation.
Okay. Okay. We'll come back to this then. So, in order to estimate this, I'm sorry, it's going to be very, very theoretical session, but that's all VCAT has. Okay. So, in order to estimate this with number of samples, now what we can do is, see, this is something we don't know for each and every arm. So, what we are going to replace it with, the actual rewards we receive after pulling the arms. Okay, but this is the way. See, if you really want to compute or estimate your gradient like this, you can still do it. Fix your theta for certain number of samples. Let's say
You're
100.
saying something, or
Am I audible or not?
Yes, you're audible.
Okay.
am I audible? Or sorry, maybe my issue.
Hey, Cyclone, you are audible, sir. I cannot hear you.
Yeah.
What about now? Hello, am I audible?
You're audible now.
Okay. So I was saying that
Who
you
is
can
audible, Nitish? Like, I can't get Sir's audio. I'm not sure why.
Same with me.
Okay. What about now?
Yeah, now I can hear you, sir.
Okay. So let's move on. So see, look at this. You can definitely compute your estimated gradient with this formula. You can keep the thetas constant for certain number of certain number of time steps, and collect these samples and then compute this gradient. But that's not how you need to do it. We look at a very powerful method which is called reinforce, which change the way this gradient descent algorithms will be used. Okay. So this formula I'm directly borrowing from Sir's slide, and I think I'll explain it briefly. So this is the change in your parameters theta. Alpha is your learning rate, how small or how large you want to learn the parameters, or how small or large step you want to take in order to learn your parameters. RT is the reward you receive in at time step t. Okay, and this is the gradient of pi theta if you take action at, and this is the policy value. Now look at this formula for a second, right? So we looked at policy gradient methods. So in gradient descent methods, one of the very popular methods was stochastic gradient descent, right? Stochastic gradient descent means you can learn from a single sample, however bad it could be, but if you keep the parameters uh, in right range, or possibly reduce it over time with appropriate speed, then you will learn the actual very close to the actual optimal parameters, right? Now the reinforced paper from Williams that came in 1992 did one more change in the formulation, which is converted this or the gradient of the policy directly the to gradient of logarithmic of the policy. There should be, sorry, my bad. This will actually make our lives very easy when it comes to actually computing the gradient that should be used to update your parameters theta. Any
But
questions?
how are the two equivalent?
They are not exactly equivalent, but how this is okay. So your question, so they are exactly not equivalent. But is your question how is this correct?
Yeah.
Okay, for that you'll have to read the research paper in detail. So I'm going to just
Okay.
borrow this conclusion.
Got it. Yeah.
Okay. Now I'll write one more variation of this equation, which involves the baseline. Okay. So this particular equation involves this particular parameter theta. So again, few things. This is your learning rate. This is the reward you receive in time stamp t. This is the gradient. Baseline says that how good or bad your reward is, basically. So let's say your average is coming out to be, for your baseline, the average is coming out to be 4.5, and suddenly you receive reward which is, let's say, -3. You can immediately say this is a really, really bad reward or bad sample, right? So -3 minus 4.5, it will become something like this, and it will, increase the magnitude by which your parameters should change. And the other way around also is true. Let's say all so far you have been receiving rewards which were negative, a -1, -2, and -3, so on, and their average is -2, and suddenly you receive reward of +1, right? So 1 minus -2 will become 3, right? So it is indicating that this is a really good reward, and it's going to increase the magnitude of changing the parameter of the or increasing the parameter or probability of that particular action. Now some terminology. This is your this is called reinforcement baseline. And this is called characteristic eligibility. Maybe I should use different. Okay, this is similar to eligibility traces that we had seen in week 6, which decides for a particular state how much uh, uh, that particular state is eligible for receiving the update from a reward. The same thing is here. Very similar thing is here for the parameters theta. All right. Any questions? No, so far, we have been doing, still there will be quite bit theory coming now, but more relevant, more easy to connect with. Let's consider the case of binary bandit problem. If we derive the gradient for some of the cases, I think it will become easier for us to identify how this works. All right. So let's assume that there are only two actions, action A or action, the other action, A is equal to 0 or A is equal to 1. For A is equal to 1, the probability of taking that action is theta, and the probability of taking the other action will obviously become 1 minus theta. Okay. Now, let's derive the formula for the gradient. Okay, assume that A is equal to 1. Then what will this formula lead to? It will become log of theta, right? If I take the gradient of log of theta with respect to theta, it will become 1 by theta. If A is equal to 0, then it will become derivative of log of 1 minus theta. That means minus 1 divided by 1 minus theta. Okay, so there's a in the lectures you will also see that there's an easier method to write it in combined formula, which is something like A minus theta divided by theta into one minus theta. See, if A is equal to 1, if you put 1 over here, then this will cancel, right? If you put A is equal to 0, then this will go away, this will get cancelled, and minus 1 by 1 minus theta. So this is what we'll get. Okay. Now, what will be our update rule? Alpha times RT multiplied by this quantity, A minus theta divided by theta into 1 minus theta. So in the lecture slide, you will find that alpha, your learning rate kind of absorbs this denominator quantity, and sir writes like something like this: rho times RT multiplied by A minus theta. See, because theta is uh, independent of your reward as well as the particular timestamp. So we can write it like this. So by this formula, rho becomes alpha times theta into 1 minus theta. Any questions so far?
It should be alpha divided by theta into 1 minus theta, no?
If rho, you are right. You're right. It should be something like this. Now, see this one. So your delta theta basically is alpha times RT. So I've chosen the baseline to be 0, A minus theta. Okay. Now, though we have derived this, let's try to, see what happens to theta by some examples. So let's say R is plus 5 and another example is R is minus 5. Okay. You take action equal to 1, you take action is equal to 0. Okay. So basically we have 4 combinations. So what's going to happen to the probabilities or the delta theta if we have these situations? R is plus 5, action is 1. R is minus 5, action is also still 1. Reward is plus 5, action is 0. Reward is minus 5 and action is 0. Now in this first case, see, alpha is some positive quantity multiplied by RT, which is 5, and A minus theta. See, theta is going to be between 0 and 1. So what's going to happen here now? I'm taking action 1. Recall that this is your delta theta. So what we can be sure of, this is going to be a positive quantity greater than 0, right? And if this is the case, then theta is going to increase. And if you go back and look at the formulation of this binary bandit, theta is the probability of taking the action A. That means we are increasing the probability of taking action A, which has yielded positive plus 5 reward. Okay, that makes sense because that is what's supposed to be. Now let's see if there is negative reward. Alpha times minus 5 and 1 minus theta. This will be your delta theta. In this situation, again, this is a non-zero quantity going to be greater than 0 quantity. This is also greater than 0. This is negative. So the overall expression becomes negative or less than 0. That means what you are doing is you're decreasing theta. That means don't take that particular action A equal to 1 because it yielded negative reward. Now let's look at the other two cases. Delta theta alpha plus 5 0 minus theta. Okay. Now this whole quantity is going to be less than 0. Why? Because theta is greater than or equal to 0 and the rest of the two quantities are positive. That means we are going to decrease theta. When I took action A, the other action A is equal to 0, I received a positive reward. I'm reducing theta, right? I'm reducing theta, and by that, this quantity will increase. And I think you can find out the later is also trivial now. This quantity is greater than 0. That means if I receive a negative reward by following action 0, I'm going to decrease the I'm going to increase the probability theta. That means reduce the probability of taking action A. Okay, does it make sense now? Do you think this is now this is actually implementable action, really?
Yeah.
Yeah.
Okay. Now let's take another example of let's say we have multi-arm bandit, and this time we don't have binary bandit but multi-arm bandits. And in that case, we represent the probabilities with in softmax fashion. Okay. So pi a comma theta, or I should call AI, will be e raised to the power theta I divided by e raised to power theta j is equal to 1 to n, the number of arms. Okay. Now we can okay, let me derive the formula for the derivative then. So long okay, so I'm taking the ln of this particular quantity, so it will become ln of theta I minus ln of sigma minus log of sigma e raised to the power theta j and derivative with respect to is that correct formulation?
No, wouldn't it be just theta I? Okay. So ln E of theta I will be theta I only, no?
Yeah, I'm going to write it
Okay.
right now. This will become just plain theta I. Okay. And since we are differentiating with respect to theta I, this will become 1 minus, right? Because this differentiating x with respect to x is just 1. This will become sigma j e raised to power theta j. And what will be in the numerator? Anyone? See, there could be e raised power theta 1, so plus e raised power theta 2 plus e raised power theta 3, right? And let's say I am just differentiating with respect of uh, theta 2. Okay, then this quantities will go away. This quantity will also become 0. Only this quantity will remain. It will become like theta 2 only. Is that correct? Yes or no?
Yes.
Right. So there might be many theta i's or theta j. There might be many theta j's, but out of all j's, there exactly one theta I, right? So it will become e raised power theta I. Okay, so this will become 1 minus pi ai. This is the same quantity as the probability of taking action ai. Does it make sense? Is this clear?
Yeah.
All right. So we can go. So this is now your update rule will look something like this. Delta theta I is equal to alpha times r rt minus r bar or whatever your baseline is, dt multiplied by 1 minus pi of ai comma theta. So this is the update rule for updating the parameter theta I, the action that you just chose, right? What about the other actions? What about the other actions? So see, remember that the probability of taking all the action, sum of probabilities of taking any action should sum up to 1, right? So if I am increasing this particular quantity in such a manner, in this manner, then the probability of taking the other actions should either decrease or increase depending upon what happens in this quantity, right? If this the reward that I receive at time t is more than bt, my baseline, that means I'm going to increase this. Okay, and if I increase this, by default the other quantities should decrease. So it turns out the formula, the derivation is very similar. There are two ways you can do it. One is theta j rt minus bt. The formula for updating the other parameters theta turns out to be something like this: aj my bad, that I shouldn't write like this. It should be capital theta to represent that it's a vector of thetas. Now, see, this thing should come intuitively. See, this quantity plus summation of this quantity over all other j's apart from I, right? This, they will turn out to be 0. See, sigma I is equal to 1 to whatever n, and the number of samples we have, number of arms we have, pi a I theta, this should be equal to 1, right? So if you sum this over all j's except I, and if you and then add this quantity, this will become 0, right? So that is what should happen, so that your updates are consistent with the the requirement that sum of probabilities of taking all the actions should sum to 1. That means whatever you are increasing over here, right, is basically what you're decreasing from other from the probabilities of taking other actions. Does it make sense? Now again, this is implementable. You can actually write code to see how this works. This actually leads you to the optimal action or not, and so on and so forth. Any questions? Sai, Kiran, Nitish, Chaitanya?
No, we can continue.
Okay. Now we've seen examples of two examples of discrete actions. Let's take one example of continuous actions. All right. So for a particular state, again, this is for multi-armed problem, mu comma sigma. That means taking a particular action depends on two parameters, mu and sigma, and this is how it is defined. Right. Now, if you want to derive the policy gradient formula for this one, what we need to do is we need to update two parameters, mu and sigma. They're unlike the previous examples where we had only one parameter. Now we have two. Okay, so first of all, let's find out ln pi. I'm just going to write like this. It will become minus ln root 2 pi. I'm not interested in minus ln sigma minus a minus mu whole square plus 2 minus sigma. Is that correct expansion? No, actually it's absolutely wrong. I wrote the
ln
formula
two-
incorrect. It shouldn't be here. It should be here, right?
Yeah.
All right. Okay. Now I can now that we have expanded this, we can actually derive formulation or change for every parameter, which is mu and sigma. let's say mu. Okay, let's start with mu. Then what we'll have is, okay, this quantity will go away, this quantity will go away. We'll only have this. So minus a minus mu whole square. Okay, 2 minus 1 multiplied by 2 over here, multiplied by 0 minus 1, divided by 2 sigma square as it is. Is this correct?
Yeah.
Right? So the power decreases by 1, the power comes in front. Okay, so 2 goes away, this will become minus, so it will become a minus mu, just a minus mu divided by sigma square.
Yeah.
All right, now let's also derive the formula for change in sigma. All right, this time will also go away, this will not go away, this will become minus 1 by sigma plus, this will be, okay, so minus a minus mu whole square remains as it is, multiplied by minus 2 sigma q. Is this correct?
Yes.
Yes.
Right? Okay, so 2 goes away from here, so it will become, and this will become positive, a minus mu whole square divided by sigma q minus 1 by sigma, which can be written as a minus mu whole square minus sigma square divided by sigma cube. This looks correct, right?
Yeah.
Okay, now we can actually finally write the formula for del mu and sigma. Change, basically the change that has to be made in mu and sigma. So for mu it will become alpha times RT minus BT. What was that? A minus mu divided by sigma square. And for this it will become RT minus BT whole square minus sigma square divided by sigma cube. All right. Any questions?
No, it's clear.
All right, great. So probably this is a this particular thing, this particular formulation, you can use for. Can you give me an example in which you can use this? Where there is a single state, or and you have option of continuous actions. Well, not exactly same state, but any particular example in which you can use this. Give me an example of continuous actions. Have you heard of a card pole problem?
Sorry, guard pole?
Card pole problem.
No.
Card pole.
No.
Okay, so I'll explain it. So let's say you have a so in order to understand it, so not going into the specifics of it. So let's say you want to balance a stick on your hand, right?
Okay.
And but the 2D version of it, right? So actually, if you keep a scale or a big stick on your hand, it's a you can the angle is not just in a 2D plane. It could be anywhere in 3D plane. So not that, but assume that it's restricted on to only 2D plane. So where you're right. So which direction you should move your hand so that your stick does not fall,
Okay.
right? You want to just keep it balanced.
But does it balance at some point?
Does it?
Does it balance at some point eventually?
Right. So it's okay. So is your question? Is it possible to balance it or not?
No. My question is there a stable state at last, or it's basically like it's going like, are we optimizing continuously to not to like keep it down?
No, it's yeah. You want to keep it stable. So you define the reward such that whenever your stick is 100% vertical, absolutely vertical, you get highest reward. That's what you want to do, right? You want to figure the agent, allow the agent to figure it out, right? So whenever it is closer to the 90-degree position, when it is exactly at the 90-degree position, you get let's say one mark or 10 positive reward, and as soon as it inclines, it is some way leaning towards the ground, but not something like this. So let's say your stick is perfectly vertical, then you give it plus 10 reward. So this is your ideal position that you want the agent to learn to maintain, right? But somehow it reaches something like this, then you give it, let's say, plus 5 reward. If it falls down, you give it minus 100 or something like this. Hello.
Got it. Yeah.
So in this particular problem, there are no discrete actions. That's what I want to explain or want to highlight. That the amount of angle so the amount of angle at which you want it to rotate, or amount of base you want to move left or right.
Can move it. Yeah. But
Right.
they are discrete, right? Action, left or right?
Left or right, but by what amount?
Okay.
Right. So it is continuous. You can of course discretize it to a limit that making it continuous is no longer necessary. Let's say left or right, you take actions in the granularity of 0.001 centimeter. Okay. It's a very fine resolution. If you take this high resolution, probably you can still manage it. But the point I'm trying to say is this is an example of continuous actions, where of course you can discretize it, but still it's an example of continuous actions.
Okay. No, or to define continuous problem, how do we? I mean, in a manner like, do we say that state should be immediately changed, or there is no stable state in between? How do we say that?
See, stable state. Sorry, I don't understand your question. Can you please repeat?
No. Like we are referring this problem to continuous in nature, right?
Continuous action, yes.
Yeah. So how do we define a problem is continuous? Like, do they have any particular patterns?
Uh, how do we define it? Is it?
Define any problem, whether it is continuous or discrete. Like maybe there might be other problem, not only this, but how do we define it is continuous or not continuous?
So you're saying that in a particular problem, whether the actions are continuous or not
Yeah.
continuous
How
or
do we?
discrete, how do we define that?
Yeah.
That's a great question. Uh, See, some answer I would say is, see, one is use representation like this, continuous actions representation. Second is discretize it if it does not hurt solving the problem too much, and you have the resources to still represent the problem in efficient manner. These two are my uh, uh, general answers. But if you have any particular problem in hand, maybe we can discuss it.
No. I mean, on in case of analysis too, like how do we analyze? Like
How
right
do
now,
we
also with this
identify?
hard
I think
problem.
Saikeet is asking how do we identify whether it's continuous or not.
Oh, how to identify whether it is continuous or not, or discrete, right?
Mm-hmm.
See, in this particular example itself, so there is no the amount of distance your hand or the base can move is not discrete. You can by just looking at the problem, I would say you can find out whether it's a discrete problem, discrete action problem, or a continuous action problem.
Okay. So within this, like this cardboard problem, like
Mhm.
we can move the hand, we can move the base unlimited, like to any location directly. It's
Right. Yeah.
okay.
So imagine, yeah. So imagine the stick is in your hand. You can move 2 feet left, 2.1 feet left,
Okay.
2.123 feet left. Right. You don't. It's you have the
Okay.
possibility.
Okay. Then it is not a definitive action. You can say like then it can be continuous.
Yeah, it's not discrete action. Yes.
Okay. No. I mean, action might be discrete, but they don't result in the uh, same outcome because left and right are discrete, right? To mention, but
Yeah.
outcome might
That
not be.
yeah. That part I agree. Whether to move left or right, that is there. And see, even if it is, uh, see, you can define the state as the angle of the pole, right?
Mhm.
Is equal to the angle of the pole with ground,
Mhm.
something like this. Then you don't have to worry about left and right. You know why? Because
It decrease or increase in the
yeah,
angle.
right. So let's say there is plus 30 degree. Okay,
Mhm.
so your pole is something like this.
Mhm.
Then your mu. So you can define it like this. So whenever there is left action, it is your the hand has to move left hand side, or your base has to move left hand side. There is negative sign in front of it. Otherwise, there is positive. Okay,
Mhm.
right? So your mu will be positive in this kind of situation. And if we take another example where the angle is minus 30 degree, right? In such case, you want to move your base left hand side. That means your mu will be negative. Let's say minus 3 feet or something like this. Sigma could be 1 or something like this.
Mhm. Okay. Yeah, got it.
What? So you don't have to worry about left and right. You don't, I mean, the formulation itself will take care of whether to move left or right. So you don't have to make any decision explicitly whether to move left or right.
Okay.
All right. Any questions? I think we are 30 minutes over our time limit. Any questions before we close the session?
One question is not with related to weekend, but do we have a revision session tomorrow?
Yes, we do have revision session tomorrow.
Okay. Same time?
Same time.
Okay.
And also, will we have some revision questions this time, like we had previous time?
That I'm not sure. I'll think of it the team and come back.
Okay.
So there is one thing that I have left, which is the last part of the week 8, which is policy gradient theorem. Okay, so just go through it, read it, and let go through the proof of it. Also, that sir is providing the lectures. If you have any questions regarding that, just ask on the discourse post.
Sure.
Yeah.
Okay.
Yeah, I think we can end the session.